Hi everyone, welcome to the seminar. Today we are very excited to have Sumegha Garg speak in our seminar. Sumegha is currently an assistant professor in the CS department at Rutgers University. Before that, she had two postdoc positions, one at Stanford CS and another one at Harvard's Theory of Computation group. She got her PhD in computer science at Princeton University, advised by Mark Braverman. And Sumegha uses computational complexity theory to answer questions in applied areas such as learning and data streaming. In particular, she's interested in memory lower bounds and theory of fair predictions. And today, she will tell us about online omni prediction. It's all yours, Sumegha.
Yeah, thank you for the very nice introduction. I'm happy to be talking within the seminar. So this is joint work with Chris, Omar, and Aaron. All of them are have joined the Zoom meeting. And so the outline of the talk would be we'll first look at the traditional online learning model, which in which we will study regret minimization. The goal is regret minimization, and then we will see what is the definition for online omni prediction, and then we will see what are the connections with a fairness notion, which is multi-calibration, and eventually we will see the new algorithms proposed by our paper for online omni prediction. Okay, so let's start. So first, let's start. What is the formally, what do we mean by a prediction task? And for this, let's look at the batch setting. We have individual outcome pairs. So individuals are represented by a feature vector, and those feature vectors are drawn from the space capital X. And outcomes, we will consider only binary outcomes in this talk. And then the goal for in the batch setting for a prediction task is to given some training data, which are like individual outcome examples. You want to output a predictor that takes in the feature vector and outputs a value between 0 and 1. And then ideally, we want this predictor to predict Y as good as possible. So in the distribution setting, let's say we are given a distribution D, and on the feature vector cross outcome pairs, then the optimal, the Bayes optimal predictor, which is given this data, we cannot do better than the Bayes optimal predictor. The Bayes optimal predictor is defined with respect to this distribution D, and for every feature vector X, it predicts what is the probability that the outcome is 1 given that feature vector, and this probability is taken with respect to the distribution D. So let's say our prediction task is you want to figure out what is the Bayes optimal predictor. This is both sample, this task is both sample heavy and also computationally heavy. Why? Because first, like now this P star, depending on the feature vector X, can be very complex. And so one way to write down the P star values would be for every X, jot down what are the P star values, and this can be infinite or exponentially long. So even to describe this P star, it might be computationally heavy. And then the second is like to figure out this P star value for every X, you might need a lot of samples. So to get around this, the main area, the focus of machine learning has been loss minimization, where instead of just trying to find the P star values, we say that we restrict ourselves to predict within a class of hypothesis. Let's call this class of hypothesis capital F. And then the loss minimization goal is to minimize over this concept class the expected loss that you see when you're predicting f of x, and the loss is measured with respect to the actual outcomes y. So this is the on very generalized form of what a loss minimization in the batch setting can look like. And these losses are the losses that have been considered in literature are very vast. For example, L2 squared loss, this would be L1 loss, and exponential loss, and so on. And then for every loss, you have an algorithm that that minimizes this. You can develop and you can ask the question to develop an algorithm that minimizes this loss with respect to a particular concept class, capital F. So this is the prediction task on a very high level in the batch setting. What about the traditional online setting? Now in the traditional online learning setting, instead of getting a distribution over the individual outcome pairs, we are in the distribution free setting. That is, at every time step t, you get a feature vector comma label or outcome pair xt comma yt. And a learner sees the feature vector xt and takes some action at without seeing the actual outcome yt. And then the loss incurred by the learner is similar to the batch setting. It's the loss for loss incurred by the action at with respect to the actual outcome, which is yt. So this is similar to the batch setting in the sense that informally the goal is still we want to minimize the loss incurred by our actions. We can think of actions as predictions, or it can be a more generalized form of predictions, and then the goal, and then at every time, but we want to do it in the online fashion. That is, at every time step we get a feature and a feature vector, and then we want to predict then and there what is the probability of yt, or like what action would be optimal to take. So as in the loss minimization, again we want to have a benchmark class capital F, and we want to take optimal actions with respect to this benchmark class. So formally, the goal here, instead of loss minimization, is regret minimization, where we want to minimize regress against this concept class capital F. And so let's say that capital T is the total number of time steps. Then we average out the loss incurred over these time steps. So these are the loss. This is the loss incurred by the learner, and this is the loss incurred by the in hindsight, after seeing all the time steps. This is the average loss incurred by the best hypothesis in the hypothesis class capital F. And we want to see that loss minimization is just this term, but in the online setting, we do not just hope to minimize loss, but we hope that our regret is minimized. That is, with respect to this loss incurred by the best hypothesis in the class, what is the loss incurred by our actions? And let's see some known facts about regret rates. So if even for very simplistic hypothesis classes, so for example, if F contains only the constant function 0 and 1, we can show that if the loss is L1 loss, then you cannot get regret rate better than 1 by square root t. So you cannot, so this is a lower bound on the regret rate. And then now there is an algorithm that can achieve square root of log of the size of F divided by t. So in terms of 1 by square root t regret for every hypothesis class capital F. Now this log of the size of F can be replaced by the Littlestone dimension of capital F, but I won't discuss these things in this talk. But in general, like, think this bound does not make sense for infinite hypothesis classes, but you can have a better bound for infinite hypothesis classes where you replace this with Littlestone dimension. So what is this slide saying? This slide is saying that so ideally we would want to play the best action. We would want to play optimal actions with respect to the best hypothesis in the hypothesis class, but we cannot, we provably cannot do that, because any online algorithm would always incur a loss, a regret rate of 1 by square root t. And then the upper bound is that if you fix one loss, which is let's say the L1 loss, then you can achieve a regret rate of 1 by square root t, as long as like the class is finite. Any questions till now?
Yeah, is there a learnability assumption on F for this?
So good. So here so let's say so here we are not talking about efficient learning algorithms. We're just saying that there exists an algorithm. So for example, the weighted just the online algorithm with experts with experts advice will get you this rate, but it requires you to store all the all the hypotheses. So its running time is the size of F.
I see.
So here I'm not talking about any efficiency here, but then you can this paper replaces this with little stone dimension, and still it does not talk about efficiency. But then there are like it's I think the I it's hard to get all the like what is it called, like have a comprehensive story about online learning here, because like for some settings, for some hypothesis classes, for some losses, there is a learnable there is a efficient algorithm, but for some of them there is not. So here currently I'm just talking about inefficient algorithms.
Fair enough. Thanks.
Yeah. But for inefficient algorithms also, you can replace it with the little stone dimension for infinite hypothesis classes. Okay, so now the question is, what if there are multiple learners and multiple learners with different losses? So the motivation for asking this question is, let's say we want to predict whether it would rain today or not. And this is a classic example for online learning, because every day you are predicting whether it is going to rain or not, and then the loss incurred and you see what is the loss incurred that day itself. So, and then this kind of prediction might be done by multiple agents. For example, a farmer or a fisherwoman or a commuter. So all these different agents are trying to predict whether it would rain or not, and trying to minimize trying to take actions that minimize their loss. So, for example, the loss for a fisherwoman would be whether it would whether there would be a wave. It would rain that heavily that there would be a kind of heavy waves in the sea. So all these agents might have different loss functions, but the idea is that we don't want to run an online regret algorithm per agent, because that might be too expensive. And this is something that is actually done in today's world, where everyone is not running their own online regret algorithm, low regret algorithm. We just look at the forecast that is predicted by some app, and then make our decisions based on those forecasts. So now the question is like, now the question is, we want to the Omni prediction asks to output a single forecaster that can be used for regret minimization for multiple losses. So we want certain properties from these forecasts such that they have guaranteed regret minimizations for various downstream agents that are using these forecasts. So another way to see this is like, we want to do regret minimization for multiple losses simultaneously, where till now we had talked about regret minimization for a single loss. So again, on high level, forecast is saying it's going to rain with probability PT. And based on this prediction PT, learner chooses the optimal action AT. So this is the setting. And now the question is, what is the guarantee that we want from these predictions PT? So the formal setting is at the tth time step, the feature vector comma label pair arrives. Then forecaster sees the feature vector xt after making a prediction PT, that, for example, the prediction PT is the probability it's predicting the probability of rain. Then after that it sees the label YT. Now the learner is doesn't really care about xt or even yt at this point. Like it cares in terms of like its loss minimization, but for its actions, it's just looking at these predictions and taking actions. So a learner with loss L, I will define this class capital L later. So let's just discuss like one particular learner whose loss function is defined by L. It uses a simple post-processing function to choose its action at the tier time step. That is, looking at its prediction, it will apply some small post-processing and take the action that day. So it's not running its own online learning algorithm. It's just using these predictions to take actions. A bit about this post-processing function. So the post-processing function is in general, in the batch setting, so this is a side note, in the batch setting, it makes sense that the post-processing function is of this form. If the true probability of rain is as predicted, what would be my optimal action? So this is like if PT was actually P star, which is the true probability of rain, then what action would I take? And that action is actually given by argmin, like the action that minimizes the expected loss when the label is drawn from Bernoulli, this prediction value. If the label was actually drawn from PT, then what would be the action that optimizes my loss? So this is the post processing function, and in the online learning setting, I think this is an aside that it might not make sense that this is the post processing function. We might want some different post processing functions because PT is not necessarily we don't think of PT as the probability of as trying to go as close to P star. There can be online learning algorithms where it is better to not predict P star, but actually predict certain different than values different than P stars and still get, like, for example, omni prediction or any kind of guarantees. So this is an aside, and we can talk about this after in the Q&A. But that is the idea behind the post processing function. That let's say it was the actual probability of rain. Then what would be my optimal action? So then the regret for these actions is given by the average regret for the learner is average regret by the actions based on this predictions PT versus the and you want to minimize them with respect to again compare it with respect to the comparator class capital F, where you are doing minimize over F the loss, the average loss, if you would have taken actions according to this class capital F. So this is the regret. So this is exactly the regret notion that we have studied till now. Just the actions are replaced by this post-processing on predictions PT. And then what do we want? This is the online omni prediction guarantee that we want. We want that for all losses in this loss class capital L, we get a sublinear regret. So a note about these lost class. So we will study that we will see that in the batch setting, the loss class considered was the convex loss, the class of convex losses, and that is what we will also study in our paper. But in general, we are saying that the definition of omni prediction is indexed by two classes. One is the loss class, and the second is the is the hypothesis class. So you want that for all losses in this loss class, when your benchmark class is this concept class capital F, you want a sublinear regret for these losses. Okay. So a teaser for this is like, it's not even clear as of now that whether it can be achieved, but it can be achieved. There are omni predictors in the online setting. And then the second thing is like, we can also achieve it efficiently. So before I go into the constructions for omni predictors for the online setting, we will look into the batch setting and see how papers studied the definition of omni prediction in the batch setting and the results for in the batch setting. Any questions till now? Okay. So in the batch setting, there are many works on omni prediction, and starting with the work by Gopalan et al., which introduced the notion of omni prediction and gave algorithms for achieving them. And then there were subsequent works. For example, one work showed that how to achieve omni prediction using slightly weaker notions of multi-calibration. And then there have been other works on omni prediction. So we won't go into these works, but just that this is an active area of research, and there are many papers on omni prediction, especially in the batch setting. So this was as I said, that omni prediction in the batch setting was introduced by this paper in 2022. And there the definition is similar to as we saw in the online omni prediction. In fact, our definition is inspired by this paper. So here, so this was the loss minimization framework that we studied for the batch setting. You have a distribution D, you have a concept class capital F, and you want to minimize the expected loss over this hypothesis class capital F. And now instead of just minimizing this loss, you want to instead output a predictor P such that for all losses in capital L, you have that the expected loss incurred by the predictor is less than the minimum loss incurred by any function in this hypothesis class. So here again, this is important because, for example, you could have had the definition where we had that so you just want to optimize over all these losses. So let's say this was the definition of omni prediction. The point is that so this might have been more intuitive, that in the sense that you want to minimize over all these losses simultaneously. That is, you want to output a predictor that minimizes these losses simultaneously. But the point is that even if p of x was equal to p star of x, that is the base optimal predictor, it might not satisfy this definition. Because for L1 loss, for example, you want to for L1 loss, that is V minus fx. Here, instead, if you're even given the p star x value, you still want to have a threshold. If p star x is greater than half, then you want to take the action 1. If p star x is less than half, then you want to take the action 0. So it's not so this loss is defined with respect to optimal actions, and the optimal actions might not be the predictions. So that's why the definition is you want to you want to do a post processing on these predictions. Okay. So this is the definition for omni prediction, and then as we said that it is not that hard to see that p star x, that is the base optimal predictor, is an omni predictor, irrespective of the loss function and irrespective of the Irrespective of the hypothesis class capital F. So for all hypothesis class and for all loss function classes, P star is an omnipredictor. But again, it's not efficient to find P star. So can we do omniprediction efficiently? So for single loss, the measure of efficiency is agnostic learning, whether a concept class capital F can be agnostic learnable. And we want to use the similar measure of efficiency. And in fact, this paper showed that if you're just looking at convex losses, then if a predictor P is multi-calibrated with respect to class F, then it is also an L, F omnipredictor, where L is the set of all Lipschitz convex losses. So convex losses is basically what we will see. It's convex in the action space. You want that. We don't care about the here we don't care about the outcome space, because outcomes just take two values, 0 and 1. Okay, so this was the main theorem by this paper, that all of us must have seen multi-calibration by now. But basically, if the predictor P is multi-calibrated, then you can just directly say that it is an omnipredictor. And the fact is that it is efficient to find a multi-calibrated predictor, because if it can be achieved as long as the concept class F is a weak agnostic learnable. So this is saying that in the batch setting, omniprediction is efficient in the sense that it can be reduced to to the problem of agnostic learning for class F. So this is the same kind of efficiency measure that we want even for the online omniprediction. Okay, so let me very briefly go into the definition of multi-calibration and multi-calibration. So I'll be a bit fast through this, because I think we have been listening to this definition for 4 years now. But let's see. So P is calibrated. A predictor P is calibrated if for all values V, that is the predicted values V, we have that expectation of Y conditioned on whenever conditioned on P of X equal to V, it's actually equal to V. What this means is that if you look at if you look at all the individuals who you assigned the predicted value V, then the actual probability of Y conditioned on that score group, it should also be V. So if you're saying that it's this person has 0.9 probability of repaying the loan, the another person has 0.9 probability of repaying the loan. And if you look at all these individuals combined, then expect the probability of repaying the loan condition on that group should actually be 0.9. That means that the prediction values are actually saying something. But calibration by itself is not enough, because what you can do is to get a calibrated predictor is you can predict mean for everyone. It's not really a useful predictor. So if you predict one mean for everyone, then it satisfies calibration. And for another disadvantage of just calibration is that for different subpopulations, credit scores might overestimate or underestimate the real probabilities. So that means that given a group, you might not be calibrated. So then so a fairness notion would be you want calibration over disadvantaged groups. What that means is that if you even condition on if you further condition on a feature on X belonging on an individual belonging to a fixed subpopulation, then also your predictions should be calibrated. So now instead of looking at the whole population, you are just looking at a subset of people, a subpopulation, like for example, grad students, and then amongst this subpopulation, when your predictions mean something, that is expectation of Y conditioned on this further conditioning on these score groups, it gives you the score group value itself. Now the question is, which groups should we predict? And the idea of this paper in 2018 was that we should protect all computationally identifiable groups. And this is the paper that introduced the definition of multi-calibration. That is, your predictor P is multi-calibrated if it is calibrated on every group that is defined by a function in this function class capital F. So think of capital F as like, ideally we would want this class capital F to be all polynomially computable functions. But mostly this class is not learnable. So we reduce the complexity. For example, you can think of it as like depth D decision trees or constant depth decision trees or AC0 or something like that. So it's some notion of measuring computability, but not the best notion that we would want. So you have that. So again, now you want that for multi-calibration with respect to this class capital F is given by your expectation y conditioned on f of x equal to 1 and predicted value being v. It's also v. So instead of conditioning on f of x equal to 1, so this is the definition for Boolean classes. You can rewrite this definition as expectation of f of x times y minus p of x should be 0. So we are just taking f of x back there and then subtracting v from here and then rewriting the definition of multi-calibration. So when we rewrite this multi-calibration definition in this form, then it becomes generalizable to non-Boolean functions. So this is something that we are going to use. And the idea behind this is that basically, given a score group, your function class should not be correlated with the outcome label. That is your definition of multi-calibration. And then this paper showed that if a predictor P is multi-calibrated with respect to class F, then it is an omni-predictor with respect to all Lipschitz convex losses. Okay, so let's move on to come back to the online setting. So in the online setting, what we are doing is we already have this connection between multi-calibration and omni-prediction from the batch setting. And we can extend this to the online setting. This is kind of straightforward. Like the fact that it is the online setting doesn't really matter. The connection still holds. But the one of the main contributions is that for online multi-calibration, before we didn't have an Oracle efficient algorithm, and this paper gives us that. And finally, we also have an algorithm that doesn't need to go through multi-calibration, which is important because, as we will see, it is important to get optimal regret rates for certain settings. Okay, so what is related work on multi-calibration? So as we saw, in calibration, if you just predict mean for everyone, then it is very easy way to get calibration. But when you're predicting mean, what is it? The mean is the mean over the distribution D. But if you are in the distribution free setting, it's not even clear that whether you can whether calibration can be achieved, let alone omni-prediction. So this paper by David in 1985 introduced this concept of calibrated forecasts, and it showed that if your predictions are actually the true probabilities of rain, then your predictions would be calibrated. Then subsequent works showed like even if non-efficient, it showed that existence of calibrated forecasters, that is there always exist randomized forecasters that on expectation are calibrated. And then there were explicit constructions by even previous works and recent works for these calibrated forecasts. And this is a recent work by Gupta et al. That showed that even gave explicit constructions for online multi-calibration. We will talk a bit about this paper result after a few slides. And then there are other related work in online learning, where what we are doing is, on a high level, we are asking that you want to minimize regret simultaneously for multiple losses. So previously there have been the discussion of simultaneous regret minimization, but in a different way. So various notions of regret in the online adversarial setting that optimize for several objectives simultaneously. For example, sleeping experts, adaptive regret, swap regret. But all these seek to minimize the same loss function on different subsequences of time steps. But where we are asking that we want to minimize different losses for the same sequence of time steps. So what is important in the online setting is that, so I didn't go into the details of, so we saw that we looked at what is the definition of multi-calibration, but of course you cannot achieve calibration or multi-calibration exactly. So it becomes important when you talk about omni-prediction, that how are you measuring the error of multi-calibration. And so let's look at this. So given a score group V and a function f, you measure the error incurred, the error incurred on group, on function multi-calibration error with respect to function f, and at the prediction score V to be you take the expectation and see the correlation between f of x and yt minus v. So if the error was 0, if for perfect multi-calibration, we would want this error to be 0. But if it is not 0, then we can measure in terms of L infinity multi-calibration. That is, you take the max over v, this error value, and then for L1 multi-calibration, you take the expectation, you take the sum over these errors for all these score groups. And for L2 multi-calibration, you take the expected L2 error for these multi-calibration errors. So this is the difference. Basically, L infinity, it is L1 multi-calibration error. So let's see how these multi-calibrations errors are connected. So L infinity multi-calibration, you're looking at the worst score group, where you receive the maximum error for this function f. And in L1, you are summing them up. So L1 multi-calibration error is always greater than or equal to L infinity multi-calibration error. And L1 and L2 multi-calibration error are, L1 is also always greater than or equal to L2, but you can have some relation in the reverse direction also by losing some factors. Any questions on the definitions of different multi-calibration errors? Okay. So this paper in 2021 gave us an online multi-calibration algorithm with the error rate of square root log of the size of f divided by square root t. So this might seem like optimal because it has this error rate of the rate that we see in regret minimization, which is 1 by square root t. So it's basically got the regret rate that the error rate that the optimal regret rate algorithms that achieve optimal regret rate. But it got it for L infinity multi-calibration error. And as we discussed in the previous page, that L infinity multi-calibration error is always less than or equal to the L1 multi-calibration error. So with some simple post-processing, we can also get that it gives us an algorithm for L1 multi-calibration error with the error rate of 1 by t to the 1 by 4. So you lose on the error rate. And why L1 multi-calibration error is important is because in the batch case, we need L1 multi-calibration error to be small to achieve omni-prediction for Lipschitz convex losses. So the previous work gives us that for finite hypothesis classes, you can achieve omni-prediction for Lipschitz convex losses with the regret rate of 1 by t to the 1 by 4. So that is what previous works is telling us. And then now the question is, can we achieve a regret rate of 1 by square root t? There are two questions. One question is, what about real valued hypothesis classes? So here we are saying that for even if the algorithm is inefficient, we get omni prediction for Lipschitz convex losses for finite hypothesis classes. What about real valued hypothesis classes? And the second is, can we get better regret rates? Because if you had a single loss, then we could have expected a regret rate of 1 by square root t, but here we are getting a 1 by fourth root of t. One of the things in the online setting, which is not a feature of the batch setting, is that there is a lower bound of 1 by t, slightly greater than 1 by square root t for the online setting. So in the online setting, you cannot achieve L1 calibration with error rate of 1 by square root t. So if we want optimal omni prediction rates in the online setting, then we must not go through L1 calibration. Okay, so we answer both these questions to some extent. So what about real valued hypothesis classes? So in our work, we, instead of going through L infinity multi-calibration, we go through L2 multi-calibration. Because L2 multi-calibration has L2 losses, and it's it's nicer to study them to get efficient algorithms. And there is a loss whenever we go from L2 multi-calibration to L1 multi-calibration, but still we can achieve omni prediction for Lipschitz convex losses because and that too efficiently, because we can achieve L2 multi-calibration efficiently. So what do we mean by efficiency? Efficiency means that we have an Oracle efficient algorithm. So in the batch case, there were previous works that showed that there is an equivalence between squared loss minimization and multi-calibration. But what you're doing is this squared loss minimization is being done for every score group. And we use this equivalence to develop a swap regret kind of algorithm like Blum and Mansoor to have and to finally reduce the online multi-calibration to solving online squared regression problem over this concept class capital F. Okay, so yeah, maybe we can discuss more about this in the Q&A. But the idea is that we are able to give for real valued hypothesis classes. Now we can get omni prediction where we don't have this polylog the size of f in the regret rate, but there is a dimension of Rademacher complexity here. And then the next question is, can we get better regret rates? So there was this work in last year by Kleinberg et al. that said that you can that gave a characterization for doing loss minimization for a class for proper losses, for a class of proper losses, and this and using this characterization we can say that it's for an algorithm to be an omni predictor, it suffices to minimize loss for a finite class of losses, and that can be done with 1 by square root t regret. So there is an algorithm that doesn't need to go through L1 calibration to achieve omni prediction. In all, this is like, so for Boolean hypothesis classes, the previous work of Gupta et al. Gave 1 by square root t error rate for L infinity multi-calibration, which gave and now which gave a 1 by 4th cube t regret rate for omni prediction, but for Boolean hypothesis classes we can get a better rate of 1 by square root t using this characterization by Kleinberg et al. And
Sorry,
then
I'm getting a little confused by the phrase Boolean hypothesis classes. Do you just mean finite?
Oh, I mean hypothesis classes, functions in hypothesis class is also Boolean.
Okay, thanks.
Yeah, so if we are restricting the functions in the hypothesis class to be Boolean, then yeah, it would be finite. Um, um, so so the finiteness is not the question there. Then the question is just like the hypothesis class is Boolean.
But Sumegha, when it's Boolean, do you allow like convex combinations of these things or something like that? Or it just has to be fx is Boolean, that's what we compete against?
The comparison is against fx is Boolean.
I see.
Yeah, it might be a small technical thing, but that is like maybe it can work for finite classes as Aaron pointed out, but it's not clear. Okay, so for infinite hypothesis classes, swap regret algorithm gets us some sublinear regret rate. So it's like the rate is 1 by t to the 1 by 8 for when the hypothesis for when you're doing linear regression. Hypothesis class is linear functions. So that's just like we get some sublinear regret for natural infinite hypothesis classes. And then the lower bound is we show that for a stronger notion of omniprediction, which is called swap omniprediction, then L1 calibration is necessary. That means that for this stronger notion of swap omniprediction, we cannot get a rate of 1 by square root t. Because of this previous work of Mingda and Greg in 2021. So this is the current picture for online omniprediction and the regret rates for online omniprediction, and the obvious open questions are to bridge the gaps between the linear between the rates. So one of the open question is, can we get tight rates for omniprediction for real valued function classes? And there is evidence that so this is a limitation of going through the swap regret kind algorithm where you cannot get better than there is a bottleneck from if you want an algorithm that reduces to swap that uses swap regret algorithm. So maybe we would need different algorithmic techniques to get tight optimal rates for real valued function classes for omniprediction. And the second question is, it's a bit unrelated to omniprediction. It's just about multi-calibration. So the in general, L1 multi-calibration is not very well studied. And if it would be nice if we can get Oracle efficient forecasters with L1 multi-calibration error rate of order 1 by t to the 2 by 3. So why is this 1 by 2 to the 2 by 3 coming in? So L1 calibration, you cannot, the best error rate for L1 calibration is this 1 by t to the 2 by 3. And there is an efficient algorithm that achieves it, but it goes through L2 calibration. But for L1 multi-calibration, we don't even know how to achieve this in an efficient way. Okay, yeah, oops. Yeah, thank you.
Thanks for the great talk, Sumegha. If you have any questions, feel free to unmute yourselves and ask.
You had volunteered. Oh, sorry.
Sorry, yeah, Sumegha, I had a question for you. This is to do with your open problem.
Yeah.
So,
can you see my slide?
It says end of slideshow, but yes, that's fine.
Okay.
So,
Nothing happened.
so basically, I'm wondering about this t to the 2/3 thing, right? Like, I almost know I think I know what you're going to answer to this question, but I'll ask it anyway. So now, we know that if you have this very stringent notion of ECE, then your regret rates have to be, they cannot be 1 over square root t. But then Mingda and his co-authors and Aaron and his co-authors show that if you have more nicer notions of calibration, you can get 1 over square root t regret rates, right? So could you hope to do multi-calibration with some weaker calibration notion with 1 over square root t regret? And maybe that gives you, I don't know what kind of omni prediction it would give you, but probably it gives you
So,
something.
oh, interesting. So I think I don't know well about this. These.
Maybe I should ask Aaron this question as well.
Yeah, that's a great question that I would love to discuss with you further. So distance to multi-calibration. Oh, okay, so there's two parts to the question. First is, what good is distance to calibration as a metric for omni prediction? I think it's fine so long as the loss functions are Lipschitz. And then the second is, okay, distance to multi-calibration. Distance to multi-calibration seems like a much, much more stringent notion than distance to calibration. One way to see this is like ECE upper bounds distance to calibration, because you can just wiggle the prediction for each bucket to the center of the bucket. But like, as soon as the buckets start like overlapping, as they do with multi-calibration, it's not clear how to like consistently wiggle an approximately multi-calibrated predictor to be like fully, to be exactly multi-calibrated without separately wiggling like every possible intersection of the groups. And so I do not know how to get root T like for that reason, basically, I don't know how to get root T distance to multi-calibration, even inefficiently. Although, you know, maybe there's a way. These are things I'm sort of actively thinking about, so they're like half-baked only, but I'd be happy to talk to you about them. You don't need distance to calibration. So for exact calibration, you might as well get it, right? So like your definition of distance to calibration is like, how much do you need to wiggle the predictors to get exactly calibrated? You don't actually need that for omni prediction. You just need, how much do you need to wiggle the predictions to be like approximately it would be enough if I could wiggle the predictions on average root, 1 over root T to get 1 over root T distance to, wiggle the predictions 1 over root T to get to a 1 over root T approximately multi-calibrated predictor. That would be enough. That might be easier to do. I don't know how to do it either though.
I see. So if distance is a tricky notion, can you define some notion of smooth multi-calibration, and maybe that's easier?
So one thing is like, so what is this distance to calibration definition?
Oh, it's basically you have a predictor. How much do you need to change its predictions in L1 to get to a perfectly calibrated predictor? So it's a more Lipschitz notion. It has its own issues, but it's at least more, it's more forgiving than this thing. And Aaron and Mingda showed that you can get regret rates 1 over square root T with this notion.
There's also this definition of U calibration, which might be, which is like omni prediction, but just omni prediction with respect to U calibration is you want to have predict such that you have minimum loss with respect to proper losses.
Right.
Yeah. So just to like continue this trend, so like the very simple algorithm we give to get root T distance to calibration, really the more atomic thing it's getting is root T distance to root T approximate calibration. And it happens that that's 2 root T distance to calibration because ECE upper bounds distance to calibration. You just add them up. That second step becomes more difficult for multi-calibration, I think. But maybe something similar would still get you, but like for omni prediction, like root T distance to like root T approximate multi-calibration might already be good enough.
Right.
And so that might be an easier target. Anyway, yeah, like I don't know the answers to these questions, but they're good ones. And if you're thinking about them, I'd be happy to talk to you about them.
Actually, I'm just glad you're thinking about them.
Okay.
Yeah, great talk, Sumegha. Thanks a lot.
Thank you.
Hey, if there are no more questions, thank you again, Sumegha, for coming, and see you all next week.
Okay, see you.
Bye.